So, good day everyone. I'm Michael Ferdinand Benitez, your today's presenter of X-ray diffraction. In this presentation, we're going to study some of the basic background of X-ray diffraction or XRD. X-ray diffraction is a laboratory-based technique commonly used for identification of crystalline materials and analysis of unit cell dimension. There are two primary types of X-ray diffraction, the X-ray powder diffraction and the single crystal X-ray diffraction. One of the primary types of XRD analysis is commonly applied to samples to obtain specific information about the crystalline material under investigation. X-ray powder diffraction is widely used in geology, environmental science, material science, and engineering to rapidly identify unknown crystalline substances, typically in less than 20 minutes. A pure, finely ground, and homogenized sample is required for the determination of the bulk composition. Additional uses include detailed characterization of crystalline samples, determination of unit cell dimensions, and quantitative determination of modal amounts of minerals in a sample. X-ray powder diffraction can also be applied to the identification of fine-grained minerals. In an X-ray diffraction experiment, a sample is placed into the center of an instrument and illuminated with a beam of X-rays. The X-ray tube and the detector move in a synchronized motion. The signal coming from the sample is recorded and graphed where peaks are observed related to the atomic structure of the atoms, of the sample rather. Most materials are made up of many small crystals like sand. Each of these crystals is composed of a regular arrangement of atoms, and each atom is composed of nucleus surrounded by the electrons. X-rays are high energy light with a repeating period called the wavelength. Since the wavelength of an X-ray is similar to the distance between atoms in crystal, a special interference called diffraction can be used to measure the distance between the atoms. Interference occurs when X-rays interact each other. And if the waves are in alignment, the signal is amplified. So this is called the constructive interference. And if the waves are out of the alignment, so as we can see here, the signal is destroyed. And this is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the electrons. Electrons occupy special energy states around the atoms. Since this is not enough energy for the electron to be released, the energy must be re-emitted in the form of the new X-ray, but the same energy as the original. In a crystal, the repeating arrangement of atoms from distinct planes are separated by distance d. So when the planes are exposed to an X-ray beam, X-rays are scattered by the distanced atoms. Strong amplification of emitted signal occurs at very specific angles where scattered waves constructively interfere. The effect is called diffraction. The angle between the incident and the scattered beam is called 2 theta. In order for the constructive interference to occur, the scattered waves must travel in alignment. So meaning the second wave must travel a whole number of wavelength. The same isa ito sa ating incidented beam or wave. Okay, in this case, one half of the wavelength is traveled on the incident side. So here, lambda over 2. And the other half of the scattered side yielding one additional wavelength. In the case of the next X-ray, so here, one wavelength has traveled on both the incident and the scattered side, resulting in two wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs will be determined from the given triangle. Okay, so the angle at the top here, half the angle between the incident and the scattered beams. The long side is the distance d between the atomic planes of the short, and the short side is the half of the wavelength. So by using sine function, we have the sine theta is equal to pi over 2, the opposite side, divided by the hypotenuse side, which is the distance d. This is equal to pi over 2d. And rearranging this equation yields an equation n lambda is equal to 2d sine theta. So it is known as Bragg's law, where n is the diffraction order. So it is named after William Henry Bragg and Lawrence Bragg, who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. So now we are going to take a look on how XRD machines use the law stated lately. First, we need to identify the basic setup for the machine. And this include the X-ray tube, the sample, mount, and the detector. In order to find the lattice spacing using Bragg's law, rotation must take place so that the X-ray can be detected at various diffraction angles. So in any XRD machine, will be two or maybe will be two or three main parts will rotate. For many machines, the source is fixed with the sample and detector are rotating. But for others, the XRD machine has a fixed sample mount, while the X-ray tube and the detector rotate about it. The advantage to having fixed sample mount is that samples are liable to slip off the stage of its rotation and the angle becomes too great. However, the rotation of the source and the detector is very demanding on the machine. That is why some of the machines have a rotating sample plate. The angle that forms between the source of the X-rays and the sample on the XRD is omega. And the angle between the detector and the incident beam from the X-ray source is theta. So here are some more parts of the machine. The X-ray tube or the source, the solar slides, and divergence slit. So which make up the primary optics. And at the center is the sample holder in a sample stage. And at the right side, itong highlighted in blue, so is all of the secondary optics. And lastly, we have the detector. X-ray tube is used for source of the XRD. This is either ceramic or glass container that has a tungsten filament that acts as a cathode. The cathode filament emits electrons, which then pass through a series of nuclear cores that accelerate them. This causes a white radiation effect. The accelerated electrons travel to a target anode material where the electrons bombard the element's atomic structure, causing secondary electron to be kicked out of the electron shell. The hole in the electron shell causes the secondary electron, which is caused by the secondary electron being expelled, leaves it in an unstable state. This is why when electrons from higher energies will drop down to fill the space. But in order for these electrons to go from higher energy level to a lower one, some energy must be released. The energy released is in the form of X-rays. A characteristic amount of radiation is emitted from the target material, depending on the energy level of the atom as well as the target material used. Typically, the target material is copper, and the characteristic radiation is classified as K alpha 1 and K alpha 2 radiation. So itong dalawa lang yung will pass, and si K beta will be filtered. The monochromator is much like the divergence slit, greatly increase the resolution of the collected data.